Right, two more circuit questions. We've got a set of Christmas tree lights with 40 identical filament lamps connected in series across the supply of 240 volts. Define resistance. Right, so this is going to be the resistance of a component. Again, we're going preposition happy here. Is equal to the potential difference across the component divided by the current through the component. So that's got that out of the way. Each lamp, when lit normally, carries 250 milliamp current. Calculate the potential difference V across a lamp. Well, we've got 240 volts, so old school voltage supply, hasn't been dropped down to 230 yet, and we've got 40 lamps. So we're going to divide the 240 volts across these 40 identical lamps. So we're going to get 6 volts across each one of them. Resistance of a lamp. So the resistance is the PD divided by the current, which is that. So we've got to divide 6 by a quarter. So that's like multiplying by 4. So that's going to give us 24 ohms for the resistance of a lamp. Right, part C, figure 1.1 shows the results of an experiment to find how the current in one of the lamps varies with PD. Right, so they've done the usual setup of draw the circuit diagram. Right, okay, we have these sort of things come up all the time. It's just so much easier to have a variable supply rather than messing around with potential dividers, I always think. So there's the variable supply, there's your ammeter in series. We're only looking at one lamp. There's your one lamp, and there's your voltmeter in parallel. Sometimes they ask you to then actually go through, what steps you'd take. Same old thing that we do for every single one of these experimental questions. You have the thing that you're varying here, so we're going to, vary the PD on this. So essentially, we're varying the EMF. Then you can measure the current, you can measure the voltage, and then you can calculate. Well, actually, we don't even need to calculate anything. You're just plotting it out. But remember, we're always doing the same things. The thing we're varying, the things that we're measuring, the things that we're calculating. And you just put them all in a table and then say how you're varying it. As in, we're changing the knob on the variable power supply, measure that with an ammeter, measure that with a voltmeter, calculate things using a formula. Gift marks all the time on those sort of questions. Not that they've asked for it here, but anyway, just thought I'd go over it again. Part 2 of C. So resistance of the lamp at room temperature is 10 ohms. Using figure 1.1, so the graph there, sketch a graph on these axes of the variation of resistance R with current for the lamp. So we know it's going to be starting at non-zero. So we're starting off here at 10 ohms. Let's go with that, seeing as that's our room temperature starter. Now we know here from this graph that the resistance is increasing with increasing current, but we don't know exactly how. We don't know if it's linear or whether we got a curve. We can't actually, without doing much more detailed analysis of exactly what's happening with the curvature of this graph here on the left. So they leave it fairly open on mark schemes. As long as it's going up, it doesn't matter if you draw a straight line or if you draw, a line that's curving upwards or something like that. It doesn't really matter, providing it's moving upwards. So just go for a straight line would be fine. So yeah, we just have something like that. Sketch a graph. Yeah, we don't have to say anything more. We just got the starting point and then the increase in resistance. Explain why the resistance of the lamp varies as shown by the graph you've drawn. Right, so yeah, this is the usual thing. Resistance goes up as temperature goes up, and the temperature goes up as current goes up, because we're getting more collisions. There are more things that are moving around, which is what happens when you start pushing the current down the wire. You've got more things moving. You're going to get more collisions between the moving electrons and the ions, the atoms in the metal of the wire. So you're going to get then greater vibration of those things, and then yeah, you're just putting more vibrational energy into the wire, which is why it's heating up. There must be another bit to this question. There is. Here we go. In an alternative design for the set of Christmas tree lights, they put in a 100 ohm resistor in parallel with each lamp. Right, describes what happens to the brightness of each set of lamps when one lamp filament burns out. Right, in the original set, because it was all just going straight series stuff, so they're all just in series, one of them blows and then the whole lot goes out because we've broken the circuit. Well, not the wire, we've broken the circuit in the lamp. So yeah, we've got everything go. What happens to the brightness? So the brightness is going to be equal to 0, as in no lamps are on. The circuit is broken. Now, what about in the alternative set? Well, we know from before that we had, what was it, 24 ohms was the resistor of each, resistance of each lamp. So if we blow a lamp, we're going to we're going to sub 24 ohm, well, we're going to sub 100 ohms for the 24 ohms. So for 24 ohm lamp. So we've got fewer lamps with lower PD, because we're going to get more potential over this 100 ohms than we did over previously when we had the 24 ohm lamp there. So we've got fewer lamps with a lower PD, therefore they're going to be dimmer but on. So that's going to be the change. That's the advantage of having these alternative routes. If you're putting them all in parallel pairs of resistor and lamp, then you know the it's just going to make it continue to stay on, but it's still not going to be as good as it would be if you had all of the lamps. Right, the last part then, calculate the current drawn from the supply for the alternative set of lamps with all lamps working. So in this case then, we've now got for all lamps working, so we want to get the resistance of a parallel pair. So resistance parallel pair, so that would be 1 over 24 plus 1 over 100 to the -1. So what we're going to have there, we're going to have, if we put that all over 240, we'd have 12.4. So 240, let's write that again, 240 over 12.4, just doing our fractions and then flipping those over. So what is that? That is going to be, if we had 20 of them, we'd have 248. So that's going to be 20 minus 8 over 12.4, which is, that's what, 2 over 3.1. 20 minus 2 over 3.1. Okay, it hasn't come out a brilliant number. It's going to be about 19.4, but I'm going to put it into the calculator anyway. And we get 19.35 ohms, give or take. So yeah, what did we want? Oh, we want the current. So the current is going to be the voltage. So the voltage is still going to be 6 over each pair, because we're dividing up the 240 into 40 chunks. So we're still going to get 6 volts, but now we're dividing by the 19.35 ohms bit. Now I've got the calculator on, 0.31 amps. So yeah, some easy enough calculations on that end to the question. Right, what we got for the other one? An electric heater, constant resistance 42.5 ohms. Interesting. We've got an ohmic electric heater connected to 230 volt main supply. So we've moved into modern day voltages. Wires of total resistance 2.5 ohms. Show that the current in the wires is about 5 amps. Right, this is all in series. So we can get the current is going to be the voltage, which is 230 volts, divided by the total resistance, which is 42.5 plus 2.5, so 45. So what have we got going into that? So 5 45s are 225. So we're going to have 5 1/9. of an amp. So 5.1 recurring if you wanted it as a decimal, but I'm going to stick with 5 1/9. I do like the fractions. Calculate the total power dissipated to 3 significant figures. Right, so our power is I times V, so that is 5 1/9 times 230. So that is going to be multiplied by 5 first, so 1150 plus 230 over 9. Yeah, let's just keep doing this as 230 over 9, so that's going to be 25 is going to leave us with 5 ninths, so 1175 and 5 ninths. So yeah, well, what did we want it? 3 significant figures. All right, so that's going to be fine. I mean, 5 ninths we know is 5 recurring on all of these, so we've got our decimal answer if we did want it, but to 3 significant figures we're going to get 1180 watts to 3 significant figures. Suggest a suitable value for the fuse in the plug connecting the cable to the main supply. Right, well, we've got 5 1/9 amps, so let's go for an 8 amp fuse. Seems reasonable, doesn't it? You get 8 amp fuses quite commonly, so let's go for that. Part B, calculate the cost of nearest penny using this heater for 4 hours when 1 kilowatt costs 21p. Right, so we've got our kilowatts is 1.18. Multiply that by 4 and then multiply by 21p. So that is 4.72 times 21p, which is, what's that going to be? Well, we've got the 4.72 plus then the 20 lots of that, which is, what's that going to be? 94.4. So we got 99.12 pence. So to the nearest penny, 99p. Then part C, the wires used to connect the heater to the supply have a total length of 9.5 meters. All right, so we need cross-sectional area from our resistivity formula. So rearranging that, we're going to have resistivity times length divided by resistance. So 1.7 times 10 to the minus 8 multiplied by the length, which is what, 9.5, divided by the resistance. What was the resistance of the wire? 2.5. Let's just check that I'm doing this for both wires. Yeah, total length of 9.5 meters. So yeah, 9.5 meters, 2.5 ohms. So that's going to be 1.7 multiplied by, oh, how annoying. So that is 3 4/5. And then multiplied by 10 to the minus 8. I'm on a bit of a roll for doing some mental maths here. So we got 1 7/10. 1 7/10 multiplied by 3 8/10 multiplied by 10 to the minus 8. So that's going to be just cross multiplying these. We're going to have 3. We're going to have 21 over 10. We're going to have 8 over 10. We're going to have, we'll put the bracket in the wrong place. And then we're going to have 5.6 over 10, mixing my decimals. And then we got the multiplied by 10 to the minus 8. So yeah, over 10, what's that? 29 is 30, 34.6 plus the 3, so 6.46 times 10 to the minus 8 meters squared. Squeezing that on. That's maybe, well, we have got 3 significant figures on all of these things, so let's keep it at 6.46 times 10 to the minus 8. Suggest and explain one disadvantage of connecting the heater to the main supply using thinner copper wires. One disadvantage, I was going to say there's no advantage in that. So yeah, disadvantage. Well, if you've got a thinner wire, so if you've got A has gone down, therefore the resistance will go up. So we'll get more heating of wires, which means therefore less heating from the heater. which isn't going to be what you want. And the whole point of having the heater is you're concentrating your power delivered to where the heater is, not from out the wires. So definitely a disadvantage there. Yeah, that was a nice question, that one. I mean, mainly just for playing around with some numbers. But otherwise, yeah, two fairly easy ones. I mean, it's nice to have some reminders on calculation questions just to keep you on the zone, keep you in the zone on those sort of things. So there you go.